Hello class, we're going to try it a little different today. I'm going to talk to you and you're going to pretend I'm here. You're going to need paper out, you're going to need something to write with, and this slideshow cannot be paused, it cannot be stopped. You're going to have to keep up, so you're going to have to write quickly, you're going to have to listen, you're going to have to pay attention, so please make sure that you're doing that. Today we're going to learn all about work and power. Work and power are nice simple concepts, you'll like it a lot. Our magic color today is green, so make sure you're writing down everything in green. If you're going too slowly, then you'll have to catch up on the notes with somebody else a little bit later, but please try and keep up as much as you can. Today we're going to learn all about work, and work in a physics sense is made up of a force and a distance. If you're not applying a force, if there's no distance involved, you're not doing work. So if you're a Burger King, you may not actually be doing work while you're working. The trick here is that the force and the distance have to be in the same direction. If they're not in the same direction, then only part of the force that we're doing is doing the work, or we may not be doing any work at all, even though we're exerting a force. If the force is applied at an angle different than the direction moved, then the amount of force actually doing the work is smaller than what we're putting into it. For instance, if you're shoving against the trunk of your car, trying to shove your arm makes an angle with the car, which means you're shoving both down and forward, but only the forward part of your arm's force is actually doing the work. So if you're shorter, then a bigger chunk of that is going forward, and we do that. We would have to use sine and cosine and things like that to use this. I'm not going to make you do that because I know most of you hyperventilate when we get into harder math, so we'll skip that. If something is falling down, even if you're pushing up on it, say I had Bob lifted above my head and I'm slowly lowering him down so that he doesn't get hurt, his weight is pushing down, I'm pushing up to slow his fall, but even though I'm pushing, his weight is doing the work because the direction is down and the weight is down, I'm pushing up. So I'm exerting a force, but the direction of movement's not in the same direction as my applied force, so my force is not doing the work. Bob's weight would be doing the work in that case. Same thing kind of happens when we're mowing the lawn. If you're mowing the lawn, the angle of the handle gets our applied force, so only that part that's going forward is going to do the work. So our applied force goes at the angle, and down at the bottom would be the part that's actually doing the work, and up the side we have just force that's shoving your mower down into the ground, creating more friction, just wasting things. So that's going to be actually harder to do. So again, if you're a shorter person, then that angle is smaller, which means the portion of the force actually doing work becomes bigger, relatively speaking. If you're a tall person, then the angle is higher and we get more wasted force and less force pushing forward. So like I tell my wife, it's actually easier for her to mow the lawn because she's short, but she always thinks it's easier if I mow the lawn than if she mows the lawn. Anyway, our work formula is clearly W equals FD. So all we have to do is take the force and the distance and we multiply them. Easy. Work is a scalar term because we're dealing with distance and not displacement. That means if I mow the lawn one direction and then shove the mower back the other direction, it does not cancel out because I still was sweating the whole time. I was still exerting energy both directions. The work is continuing to add up. So work is a scalar term, not a vector term. We do not care about direction, which is good for a bunch of you because you never pay attention to direction anyway. Our example problem. We're going to push on a mower, so 945 newtons of force is shoving forward. How much work is it if we mow 12 meters of lawn? I'll give you a couple seconds to write that down, and then we'll continue. Do 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 do. Do you feel like you're on Jeopardy? Okay, we know that 945 newtons has to be a force, because newtons always tells us it's force. 12 meters, of course, has to be a distance, because meters is always distance. I know some of you are going, how do they know? Everybody else memorized it a long time ago, and you should have too. We're looking for how much work is being done. So we're looking for W. Do we have an equation with W in it? And of course the answer is we just got that equation. So we know that W equals FD. I know the F, I know the D. All I have to do is multiply these. So you shove those into your calculator and you say 945 times 12 gives me 11,340. Now what do we put for a unit? Well, I multiplied a Newton times a meter. If I multiply a Newton times a meter, then the unit is going to be Newton meters. So the unit for work is Newton meters. Of course, there's only 2 sig figs in the 12, so I'm going to round that off to 11,000 Newton meters. Now, Newton meters is a little weird sounding, so we have another way of writing Newton meters, just like we have another way of writing a lot of units. So the other way of writing Newton meters is joule. The unit joule is named after a scientist named James Joule, and James Joule was a famous scientist that dealt with energy. And so we named the unit that deals with work and energy after James Joule. Now, joules are fairly small amounts of energy, and a lot of times we're dealing with larger units, so sometimes we use kilojoules. If you have kilojoules, kilo means 1,000, so anytime you see a kilojoule, that means it's 1,000 joules. So instead of writing 11,000 joules, we could have written 11 kilojoules, and it'd mean the same thing. So don't freak out if you see kilojoules. Any questions on work? I can't answer them for you anyway, so you're stuck. Hopefully there are no questions. It's pretty simple. So we're going to move on to power. Power, of course, is related to work. Power is how fast I can get work done. If I have a more powerful motor, that motor can either do more work in the same time, or it'll finish the same amount of work in a shorter time. For instance, my brain is more powerful than your brain is. So if we're doing the same problem, I do that problem in a shorter time period than you do. You will take a longer time because your brain is less powerful. Or if both of our brains are working for 10 minutes, I got more work done than you did. Get it? Yeah, the two factors involved here are clearly the work and the time. Now, the relationship with work is direct. The more work I do, the more power I have. They both get bigger. That's direct. The relationship with time is inverse. If I have a big time, that means I had a small power. If I have a small power time, that's a big power. So that's an inverse relationship. So the formula has work on the top and time on the bottom. So P equals W over T. W is work, T is time. Work is going to be in joules. Time is going to be in seconds. So that's all normal. But of course, since work is equal to force times distance, we can also write power as force times distance over time. We pull out the W and we put in what we just learned W is equal to, F times D. So if I gave you the F and the D and the T, you could plug it straight into the bottom. If you already know the work, you could just plug it in the top. Either way, it's a really simple equation. Both of these equations, by the way, do show up on your tax worksheet. These are both tax equations. They're both cake. Everybody will do great. Let's try our example problem. If we have a 736 Newton person running up 20 meters of stairs in 8.35 seconds, what is his power? And again, I'll give you a couple seconds to write that down, but it should only take a couple. Hopefully you guys are being excellent and kind and nice to the substitute, and you're obeying, and you're in your seat, and you're doing what you're supposed to do. Of course, we look at the numbers and we see 736 newtons, and as soon as we see newtons, we should think of force. Then we see 20 meters, and as soon as we see 20 meters, we should instantly say to ourselves, hey, meters always tells me distance. Then I give you 8.35 seconds, and you say, hey, seconds is a unit of time. So if I'm looking for power, again, I have two formulas that came up like that. I'm going to use the second one, not the first one, or I could use the equation that we learned before for work and then do that. So actually, let's do it that way because that gives us more practice using our work formula in case you were slow. So the work done is going to be, if I'm running up the stairs, I have to lift my own weight. So the force is going to be my weight, and the distance is the height of the stairs. So my weight is 736. The distance was 20. That means I did 14,700 joules of work, and I did that work whether I ran, walked, or crawled up the stairs. If I ran up the stairs, I did it faster. If I crawled up the stairs, I did it slower, but I still do the same amount of work. Now, since I gave you a time, power, of course, is work over time. So all I do is take the work answer that I just got and divide it by the time, and that'll give me 1,760 joules per second. The unit for work was joules, the unit for time was seconds, so the power unit must be joules per second. Now again, a joule per second is better known as a watt. A watt is named after a different scientist named James Watt, and James Watt was a guy who kind of refined the steam engine into something that was very useful. So our use of machines to give us power and things like that, we can all thank James Watt for that. So you probably heard of watts. That's the unit of like light bulbs and stereos. There's all kinds of things that are rated in watts. That tells you the power of something. And again, a watt is also very small a lot of times, and so we deal in kilowatts, and kilo again means 1,000. So anytime we see something that's in kilowatts, it just means 1,000. So if we have 1,760 watts in our previous answer, we could write it as 1.76 kilowatts, because kilo means 1,000. So we're just making it 1,000 times smaller and sticking that K in the place. Sometimes that makes it easier. Things to remember. 1 Newton meter is equal to 1 joule. 1 joule per second is equal to 1 watt. As long as you remember a watt is a joule per second and a joule is a Newton meter, it makes things easier when you're converting, when you're moving stuff around. The problems are pretty much this simple. I'm going to give you some homework. You're going to have a chart on the bottom of the homework where I'll give you some of the answers, and you have to find the missing stuff. So treat each line like it's a problem and just figure out what's missing. You should be able to handle it no problem. For homework, of course, we're going to do problems A. When you're doing problems A, I would love you to work in small groups. I want you to work together. I want not one person doing it and everybody else copying. I don't want you playing Angry Birds. I want you to work diligently in your small groups. There is a lab on the back of that sheet. We will not be doing that lab today. We will do that lab when I come back on Monday. So please get started. Have fun. I miss you too. Bye-bye.